Please welcome to the stage Associate Director for Networking at the U.S. Department of Defense HPC Modernization Program Air Force Research Laboratory, Ralph McEldowney.
Good morning, SC25. Let me congratulate Kevin and the SC26 committee on a fantastic launch this morning. We will see them in Chicago. Welcome to our invited talk session on applications. We have two outstanding talks for you this morning. Our first one will be on egocentric video understanding. And our second talk will be on the use of HPC for the design of jet aircraft engines. Our first speaker this morning is Dima Damen. Dima is a professor of computer vision at the University of Bristol in the UK and a senior research scientist at Google DeepMind. Dima's research interests are in the automatic understanding of object interactions, actions and activities using wearable sensors, and is best known for her leading research in egocentric vision. She is the project lead for Epic Kitchens, the seminal data set in egocentric vision. At the University of Bristol, Dima leads the Machine Learning and Computer Vision Lab. At Google DeepMind, she is part of the Vision team, focusing on video understanding research. Please help me welcome to the stage Dima Damen.
Good morning. Thanks, everyone, for staying around. And hopefully, you'll be able to find something interesting in this topic of egocentric video understanding. I know this is not a specialized computer vision audience, so I will start by motivating why is this an important topic. Actually, the term egocentric is we're used to it. And we know it because it relates to this idea of understanding one's self-importance or self-esteem. But when we talk about egocentric vision, we really want to see the world from the same viewpoint that you would be seeing the world from, as if you're having a camera observing the world from your eyes. And what's important here is we don't want to understand the world, we want to understand the camera wearer. So through observing the world, our objective is to understand what objects the person is interacting with, what actions, and importantly, what intentions do they want to form through observing the world from the egocentric perspective. And while this is kind of the research question, the motivation really stems from the current status quo. This is a nice illustration by a Spanish artist that observed a number of people going down the staircase and observed where we currently are. We are stuck with this handheld computer device known today as the mobile phone. And people make lots of memes about how stuck we are and how important it is for us to remain connected. Those who work in egocentric vision believe this is the present, and the community is very much ready for the future, where we have our hands free again, not to be stuck with these mobile devices. Once we have this wearable computer that still enables us to remain connected, because apparently we would like to, but also gives us this ability to interact with the world the way we used to before mobile phones came to play. A number of players have been coming up with what I would call early prototypes. And the Apple Vision Pro was the first commercial product that you've heard about that could potentially form the future of wearable computing. And of course, all of these are early prototypes. That's why I say there are always brave souls who start using them early. And we will find that odd, but in the future, this will become a norm, in addition to the change in the actual hardware form, in the form factor of these devices. And people start capturing and observing others as they start using these devices. And my favorite is this one. And if this is a future you do not want to hear about, and it's a scary future, I would just want to remind you about technology and how it evolves. 45 years ago, when Sony came up with the Walkman, there was a huge backlash from the community. There were terms around banning the Walkman, calling it a menace, also saying we will be lost in a world of our own, and this will be a mind-altering machine. 45 years later, I think we all maybe some of us still believe that our headphones are mind-altering, But this is an accepted technology that most of us use as we walk around. And also to give you an understanding of how slow technology is. We're all in a field where we claim technology moves very, very quickly. But the timelines always remind us that things really move slower than we claim or imagine. I'd like to put the original first wearable camera to the 1907, when pigeons were equipped with cameras to be able to still have their hands free and fly around, crossing enemy lines to capture what's happening at the other end. Slowly and over time, people started wearing cameras even before the form factor became viable. This is a picture from 1987 of bikers who started wearing actual standard cameras on their head to be able to capture their sports versatility and the agility that they perform. In 1995, this is Stephen Mann, who's well known to be the person who was wearing these devices and going around. He, amongst others, were also the people behind the eye trap, which was this idea to keep one eye open and one eye to become the one that will be able to capture the AR or the VR of the future. And significantly years later, these three same technologies started evolving into products. So the GoPro, which now is the one that people use when they want to capture sports, came in 2004, significantly later than the 1987 early prototype. The Google Glass in 2012 is very much a replica of the eye trap. And one could argue that the Apple Vision Pro is not very far from Steve Mann's early prototype. So really, it's always a good reminder between the early prototypes of computers and how long it takes for them to become even the first encounters of still early prototypes in viable commercial hardware. So with that as a background, and if I convinced you that egocentric cameras will be part of our future, my work is to look at the types of footage that we can capture out of people wearing cameras, and hopefully this is playing smoothly for you. These are the types of footage we capture by giving people cameras and asking them kindly if they would capture bits and pieces of their daily life. This captures the hobbies, the mundane tasks, the ordinary routine, as well as skilled activities that they might be performing. And if this is a short snapshot of their life, typically what we have is a very, very long capture of one's life, hours and hours of what someone would be performing. And this is where our need for really supercomputing. We are having hours of high-resolution footage that until today we cannot yet put into any hardware, into any actual architecture. Over the years, I've been involved in a number of data collection exercises where we give people cameras and ask them to record footage for us. This started in 2017 with Epic Kitchens, where we asked people to focus on kitchen-based activities as one of the hardest skilled activities that all of us perform. It has a lot of tools and a lot of interactions with objects. After Epic Kitchens, I co-led a big collaboration of 13 different universities where we worked with 923 volunteers who all captured different types of their lives between 2020 and 2022. At that time, there wasn't yet any of these form factors to give to participants, so we relied on the GoPro. In more recent work, we are using some of the research prototypes. This is Meta's Aria glasses, which is a research, not a commercial product, a research high-sensored prototype that we use for capturing devices. And we've collected a data set called EgoExo4D, so that has exocentric cameras and egocentric cameras focused on skilled activities. And I'll tell you more about our most recent release called the HD Epic dataset. Why do I talk to you about data? Because clearly, currently in machine learning, if you have no data, you have no machine learning. You have no learning of any sort. We are reliant on large amounts of data. So the current paradigm in computer vision or machine learning centers around wanting to do some research, and the first question is, can I find a data set that allows me to do my research? You would then go through this exercise of training a model and observing the performance of this data set over time, and your hope that this test error guides the progress of your architectural modifications. While the data set can actually be labeled or unlabeled, currently there is research on self-supervised or unsupervised learning, we still need a labeled test set to guide the progress of our architectural progression. We still need numbers to tell us we're going in the right direction. So labels remain key in anything to do with machine learning or computer vision. And between data and labels, there are currently two huge paradigms that I think you should be familiar with because they're very distinct. The first is labels to data. If you want to do a task like object recognition, then you go and say, OK, let me find some labels for objects. And the famous ImageNet dataset that you might have heard about centers around going to WordNet, which is an architectural distribution of words representing objects in the world, and then selecting a particular level of depth in WordNet, going around and searching for these words on the internet and coming up with a data set. So this is the paradigm of going from labels to data. This paradigm is very different to another one that goes from data to labels. So the Kitty data set and almost all work in autonomous driving doesn't go and say, OK, let me collect 10 examples of turning right and 10 examples of turning left. Instead, they put cameras on cars and let the cars drive. And the outcome is a huge amount of data, which is unlabeled, but hopefully has all the representations they were interested in. When we started working on egocentric videos, we had to decide which of the paradigms to go with. And we opted to collect data first. That means we actually gave people cameras. We told them, please don't change anything you do in your daily life. Just put this camera on and start recording every time you walk into the kitchen and stop recording when you walk out, giving us this wealth of representation of people doing stuff. But we had no idea before the data came back to the lab what this stuff is. Critically, we had no idea how to convert it from this wealth of videos and hours into something we can put into training or testing. So we came up with this idea of actually borrowing information from movie data sets that come with scripts. And we started scripting our data. We asked our participants to watch their footage after recording and to give us a live commentary of what they actually are doing, giving us something that first looks like freeform, which we then refine into segments, and allowing us to convert this footage into data that we can use to train. But importantly, this is actual representations of what people are doing. So if you wanted examples, as you see here, of opening ovens, this was part of a normal activity, but part of it is opening ovens. Critically, when you go from data to labels, you come up with something that is heavily long-tailed, because that is the natural occurrences of actions in the world. So the y-axis here is log-scaled. You can see that this is really heavily long-tailed. You have a lot more examples of someone taking or removing something than lifting or choosing. And this comes with a huge challenge, but is a particular critical component of the data to labels. We followed over the years with the large-scale Ego4D dataset. We did the same thing. So we asked people to record footage uninterrupted, and then we equipped this footage with narrations, you can see at the top, collecting 3.8 million sentences of how people perform stuff all around the world. This effort involved 13 universities in 13 different countries. So we collected people with these descriptions of how they are performing daily activities. And this power between linked text and video enabled us, as well as others, to really use this footage for lots of potential applications. The bottom one, so the R3M paper, is the first paper that used Ego4D, the dataset, to pre-train for robotic manipulations, showcasing that such imitation learning from humans, even though it's completely unscripted, gives you a power to increase the representation for robotic learning. So to go back, the first question we ask in computer vision and machine learning, what comes first? The labels or the data? Do you go from labels to data, or do you go from data to labels? And really, you have two different camps in which one is the right one to go forward. So the chicken or the egg, the data or the labels, really the one on the left gives you naturally unbalanced data set. You have occurrences that match what you'll see in real life, which some machine learners don't like. They like data to be balanced or unnaturally balanced. And that's if you would get that if you start with the labels first. Starting with the data first is harder to label, because you're going to look at this mess and say, how do I give it meaning? Starting with the labels looks easier to label, but actually it hides lots of ambiguity. You say, give me 10 examples of a chair, but you don't ask the alternative. If I look at the image, would I label it a chair? Importantly, the data first is closer to applications. And people credit the success of the autonomous driving industry to the fact that they started data first. if they had collected 100 examples of turning right and 100 examples of turning left, they probably would be very far from making this now applicable. However, one of the challenges of data first is that it cannot be expanded. You can record another 10 million hours on the road and not have a single accident, which is data that you actually need to cover the tail. If you start with labels first, you go and collect 10 examples of a particular label that you want. Data or labels first is one of the key questions that remain to be asked or answered in machine learning. And while I told you that no data, no machine learning is key to us, actually you also know that no supercomputing, no machine learning. And we are heavily reliant on the usage of these huge supercomputers. I'm here thanks to the introduction of the Isambard AI supercomputer at the University of Bristol, funded by DCIT, by the UK government. And this is really fueling the research we're doing. If you've been around for SC25, sorry for the typo, you've seen a lot of examples from BRICS, the Bristol Center for Supercomputing, where they were presenting the foundations, we're just users, the foundations of the infrastructure of the 11th fastest public supercomputer. And I believe later today, one of our superheroes, and I believe yours too, Professor Sadaf Alam, will be talking about her experiences. Having motivated egocentric computer vision, I want to tell you about some of the research that we do. So we have all the data, we have all the infrastructure, and I'll spend the remainder of the time giving you an overview of some of the research that we do in egocentric video understanding, and I'll start by the richness of the audiovisual nature. Videos are really not silent movies, they are highly multimodal. And in egocentric videos, we have very, very rich audio because the camera travels with the microphone towards the action, giving us an understanding of object-object interactions like this. Hopefully, you'll be able to hear the audio. No? OK, we did check this, but let's check again. OK. I think if we can make it higher, it will be easier. So you have lots of object interactions. You have lots of material sounds. And you also have these objects that actually are sound emitting by nature. So one of the interesting questions is, how do you deal with this multimodal input? To date, the standard way is to look at the video and the audio and provide labels to what both combinations provide. Say in this segment, the person is washing a carrot or washing a tomato. And then you feed both modalities to what's called the multimodal model and hope that the output matches these labeled segments of data. One of the challenges in putting audio and video like this is that the assumption that the audio can really come up with these labels is an incorrect one. For example, it is impossible from the audio solely to know whether someone is washing a carrot or washing a tomato. Some actions are by definition silent. So we started this adventurous approach to look at what you could recognize purely from the audio. If you gave a human just the audio, what can they label in terms of a start and end time for an action and the semantic of that action? And I'll be able to show you some examples of what humans labeled purely from the audio. You'll now see the combination of the visual label and the audio label. There are lots of things you can absolutely recognize, but not in exactly the same semantics. Then the question is, now having produced a data set that's labeled in two ways, the visual modality is labeled using visual semantics, and the audio modality is labeled using audio semantics. What do you do with that? We are not used to this. Typically, we're used to two modalities as input and one semantic space. Here, we have two distinct semantic spaces. So last year, we presented the first approach to try to understand this audiovisual input using two different audiovisual semantic spaces. And the approach goes like this. Oops, OK. So the input is you still want to give both modalities to your transformer, if you're familiar with that, or your multimodal model. But we want to actually be querying it with a different start and end time and a different semantic modality tag to say what is happening between this time and this time if you focus on the visuals. So you come up with a visual action. The same model should be able to take a different start and end time and be told, OK, now could you focus only on the audio? And can you give me a representation in the audio semantics? So this is exactly the same model, but is able to take different querying periods with a modality tag and to be able to produce an output that says, if you focus only on this, you will be able to recognize the audio semantic or the modality semantic. This is the first attempt to look at multimodal inputs with multimodal semantic outputs. I'm going to give you a tour of things, so these are not detailed. I'm assuming you're not interested in the numbers or exactly how we outperform the state of the art, but maybe in what potential applications we have. And this paper is from a couple of years ago, but it does show the complexity of egocentric videos. This is a cook cutting in a kitchen setup. This is a mechanic cutting in a mechanic workshop. And this is a construction worker cutting. We all are able to map this to the word cutting, regardless of the fact that they have different objects and, importantly, different tools, because we are able to generalize the notion of cutting into the idea that you start with something whole and you end up with something in 2 or more parts, right? That's how we kind of generalize the concept. But visually, it's very, very challenging for models to be able to do that. Particularly at times, you can't even see the wire in the mechanic setup. And if you look at more and more of what we call scenarios, you'll see that you use scissors when you cut in arts and crafts or pliers in gardening, and we're smart enough not to mix these. So you're not going to use pliers for cutting the carrots or an angle grinder for cutting paper. Interestingly, similar to this complexity when we talk about scenarios, there is a parallel complexity when we look at locations around the world. So this is a cook in Italy, actually, cutting a carrot. This is a cook in India, cutting fruit. And just by a quick observation, I hope you can see the distinction between the actions. In the left, the fruit or the vegetable, the carrot is actually static, and the knife is moving. But on the right, the knife is static, and the fruit is actually moving. And talking to people in India, they will tell you that this is a much cleaner approach to cutting because they don't need chopping boards. But to us, it looks very dangerous because the fruit is actually moving towards the knife, and we're not used to that. These are subtle differences, but they extend in all aspects of our daily life. So we looked through the Ego4D data set, which I told you about. We collected in lots of locations, and we wanted to ask, can we actually generalize? Can we understand cutting, regardless of whether we've seen a location or a scenario? Remember, all our data is heavily long-tailed. So you have a log y-axis here, but you can see that the same action, for example, cutting or pulling or turning, exists in all these individual interesting scenarios, ranging from cooking to building to cleaning, et cetera. So in this work, we wanted to really test generality by taking a combination of scenario and location. The intersection between the two will form what we call our test set, but importantly, we will remove from the training set all examples of cooking and all examples collected in Japan. We have lots of examples of other activities in other parts of the world, and we still want to generalize to the action cutting, having never seen anything in Japan or anything that is cooking related. And the approach to do this is one of those interesting approaches in machine learning. I'll tell you, this will be the only technical bit for those interested. We actually look for other examples in the training set. So we have lots of diversity in training, having removed cooking in Japan. And this comes from a diverse set of scenarios. What we aim to perform is to wonder whether if I hid or kind of not have access to the video of someone cutting lemon, can I reconstruct it from other examples that exist in the training set? And we refer to this as the support set. Can I come up with something that combines this notion of cutting from one place and this notion of oranges from another place? Can I combine the information in a way that allows me to know that someone is cutting lemon? If I can do that in the training set, I have a much better chance to actually generalize when it comes to the actual inference in the test domain. So what we do is we train this magical F and hope that once we pass through it, we can generalize to unseen scenarios. And we do that by having these examples in the support set. And then we have this matrix that says you can reconstruct one example from other examples, but having the diagonal blocked out. So you cannot reconstruct any example from itself. You can only reconstruct it by linear combinations of other examples in your batch. And this combined inventive combination should be able to match the description, someone is picking tomatoes, and should also be able to classify the action pick. We backpropagate this, so we kind of train this on lots of examples in the training set, keeping samples of support sets and saying you cannot reconstruct the video from itself. And our backpropagation is primarily to train this F. We want during inference that once we pass through F, we have removed all the information that is specific to the location of the scenario and became general. And indeed, that is also really interesting compared to a number of approaches that I know you probably are not familiar with, but just to say that this is really giving us a significant boost across a large number of test examples. So this is playing in the US, having never seen anything in the US or anything related to playing. However, this remains a significantly challenging data set. You can see that we're still on the 30% accuracy compared to maybe some of the scenarios you've seen. Hopefully, I haven't exhausted you yet. I will be on time, don't worry. But I wanted to show you some of the other things that we're looking at, particularly looking outside the video frame. This is the footage I told you about, where we are collecting data in the home. We are now able to lift this data to 3D. The only input we have is the video you've seen. We don't have anything else. We're now able to reconstruct the static part of the scene and know where the camera is over time. This is something we as humans are able to do, but to be able to do it completely from the video is very challenging. If you are familiar with 3D reconstruction, you know that this works only in static scenes. And here, everything is very dynamic. There are hands and objects moving and cupboards opening. So to be able to still reconstruct the static scene from a dynamic setup was a challenge for many, many years. And it took a nice collaboration between us, Naval Labs in Europe, and Oxford to come up with a solution that can reconstruct this part of the world. And now we are able to, having started from an egocentric setup, we are able to actually do all sorts of exo setups. So we can have like a static camera that understands where things are. So you can see where the hands are in 3D, having only looked at the environment. And we can do dynamic novel synthesis, as if you have a fixed camera in the scene, and we observe the change that you are doing over the video. Having built a static representation of the scene over many, many scenes, and now we have, I am never bored of looking at these. Having looked at the videos for very long, to be able to lift them to 3D was such an exciting opportunity. We now move from building a static part of the scene to actually tracking dynamic objects in 3D. This is a very early prototype, so what you'll see are these neon blobs that say something is moving. We haven't given it any name or any full structure, but we can track it in 3D and know where objects are. Importantly, as people put objects down and move around, which is something we always do in egocentric setup, now the system is able to keep these objects in mind, hence our term out of sight is not out of mind. So we're now able to track these objects in 3D and know where they are relative to the camera operator. And accordingly, we can answer questions whether an object is in view or out of view, whether it is in view but occluded by an object, and also importantly, whether it is within reach but not within view. Can I still extend my hand and reach it? This notion of reconstructing what's not inside the field of view is picking up massively. This is a work from Berkeley called EgoAllo. OK, this got stuck. OK, where we are able to reconstruct the full body from the ego camera. I'll just move you through to see examples. So now we are only seeing the individual image, but we are able to estimate where the full pose of the body is over time. Not only we're able to estimate the full body from this censored camera, but in our recent work, we're also able to anticipate where your hands and objects will be, which is critical to lots of safety and secure performance, particularly in industrial setups. So in this work, we call the invisible ego hand. Knowing where the body is, we can also approximate where the hands are, even when they are not in the field of view. So on the left, you see someone dancing, and we're able to estimate their full body and also forecast where their body and hands will be in the future. I'm going to jump a little bit and shift my hat to the Google setup, having been introduced that I'm a senior researcher at Google. This is not my work at Google, but this is an important perspective. Some of you might have heard of Genie 3. And Genie3 is this model that you can interact with it. It is a generative model, but these actions you see here are actions that the person interacting with the scene can press. So they can say, move left, move right. And what's interesting is that this generative setup is consistent over time. I can turn away and turn back, and whatever I painted on the scene or whatever I performed remains consistent. My favorite example is this top right example of painting, because just maintaining where that paint in 3D is, as you look around, is such a critical and really difficult task, particularly if you are not building a 3D representation of the scene. And in Genie, there is no 3D representation of the scene. This is purely a generative model. Genie3 is a new frontier of what people now call world models. From a text prompt or a starting image and video, it can generate a world you can interact with in real time. And this remains consistent for several minutes. And crucially, this consistency is an emerging property. A 3D representation of the world is not explicitly built. It's an implicit outcome of learning. OK, I told you about lots of data sets, and I will conclude by showing you how we collect data sets. We actually give people this nice backpack and ask them, are you ready to volunteer and collect some data for us? We work in households that do not have children for consent purposes. But we give them this backpack, and we tell them, go home. Once they open it, they find lots of devices and some instructions. And they were left with one key instruction: start recording every time you walk into the kitchen, and stop recording as you walk out for 3 consecutive days. In our newest data set, we want to really give the data set the highest level of labels or details to enrich future research. So we first ask participants, after they have finished their collection, to tell us what recipes they have cooked. Then we label over time the steps of the recipe and any corresponding prep that they're doing to achieve those steps. All ingredients are weighed on screen, and we label when they are added to a recipe. So basically, once they've cooked something, we ask them to go online and give us a closest recipe to what they cooked, and then give us what modifications they have done to that recipe. Then we go and label manually where exactly they have performed every step and every corresponding prep. And this causality is really rich and new. For example, in the first example of cooking a pasta in a pan, the first prep of picking the kettle to fill it with water is very relevant to that step. And current approaches haven't labeled that causality, which we've now labeled in our newest data set. As I said, every time an ingredient is added, it's weighed. And every time it's added to the recipe, it's also labeled in time. In addition to the high level of understanding activities and recipes, we understand actions in a higher level of details than we've ever done before, and as well as why people are performing actions and how. We also label the audio in the same way I've shown you before. But I'll show you some of the detailed narrations that we have now provided. I've showed you the original narrations. We had these single sentences we've built with Ego4D. And now, with LLMs and VLMs improving, we really wanted to test their ability to actually explain the actions in a lot more details, how people perform it, in exactly what capacity, are they rotating things clockwise or anti-clockwise, et cetera. Additionally, we are tracking all these objects in 3D. We built a digital twin of all these kitchens. So what you see is the video that we have collected. We've actually worked with an artist who looked only at the video and then was able to build the original CAD models of these kitchens with all drawers and cupboards in space, allowing us to track these objects in 3D. So we now, you remember our neon bulbs? This is now ground truth data of all object movements in all the kitchens we've worked with. Having built this highly detailed data set, the question is, OK, how good are we at the moment in perceiving these levels of detail? So we move from, I'll let you just see some of the examples. So you can see different kitchens here and also different movements of objects. We are labeling every tiny movement of an object, even if it's like a spoon. We enrich the data set with a VQA, so a video question answering benchmark, that tests based on everything we've collected. How do current models perform? And they do not perform well. For example, if you ask them, how exactly is this person performing the activity. The models will all know that you're washing a cutting board, but they will not be able to identify that you're rotating it to actually wash the backside. This shows the current limitation of current VLMs. Or if you ask questions like, how many times have I opened this particular cupboard in a 40 minutes video? This actually doesn't work. I'll pause for a minute in case you want to look at the data set. Our colleagues at VGG have built this searcher called Miro, where you can go and basically type something and say, give you examples of someone, I don't know, opening cupboards or cutting carrots, and you can quickly search the data set and see what it contains for yourself. If this is interesting, inspiring, or maybe scary, I advise you to look at a recent survey we've written. It's not a normal survey. We call it an outlook into the future of egocentric vision. And the first part of this survey is envisaging what the future will look like from our perspective as researchers, before analyzing the gap between this ambitious future and the current status of research. We imagine this Ego AI device, and we imagine it equipping or being in the hands of a different type of, a number of people around the world with different jobs. So for example, I'll tell you about one of our stories. We worked with a sketch artist who drew these stories brilliantly. So Sam is going home after a long day, and he has this Ego AI device. It's really good because it knows what they ate throughout the day and what ingredients are they still missing to match all the complementary nutrition they are in need of. It also knows what's in their fridge, so it advises them that the right thing to cook today is a tomato soup. It then takes them through the exercise of cooking it in a very enjoyable, audible 3D projection, and it tells them how they can perform a recipe that they might not know how to do. It's very good with giving them reminders and maybe adding some suggestions of how to improve the taste. After cooking their perfect tomato soup, it can take them back to an experience they had last summer to have their tomato soup on the beach where they enjoyed a bit of time before, having relived some of their own memories. It also enables them to play with others who have other Ego AI devices in a way that feels like they're all sitting around the table and playing cards. By the end of the day, they might connect with their doctor and say, oh, there's a bit of an itch. Can you give me advice? The device also suggests whether they would like to share some clips from their day on social media, and they decide not to. This is one of the stories you can read. There are lots of stories like Judy, the policeman. And I would be very keen to hear whether you think this is a scary future or an interesting future. And we've heard combinations of both. It's called an outlook into the future of egocentric vision. I hope this was interesting. I told you about opportunities in egocentric video understanding. I've given you really a quick tour. I'm lucky I can speak fast, so I can really take you through lots of things. But of course, I get the privilege to come and present this work, and this is the work of a great team at Bristol that works tirelessly. Everybody at Bristol is working on egocentric video understanding, and I'm grateful for all their efforts. And special thanks to the organizers for inviting me to talk to you about this, and I'm happy to take any questions.
We have time for a couple of questions. If you'd like to ask Dima anything, please come to the microphones in the front of the room. We have them in each aisle. Maybe while we're waiting for someone to come up, we have an online question, Dima. What are your thoughts on this data eventually being used to program machines and robots to do what humans do? How can we make sure this is done ethically, unlike how art was illegally gathered to create art generation AI?
I think a key thing to making sure we're doing it ethically is that the fact that we are doing it in a university and this is open source and everybody is knowing what we're doing. Without doubt, there are people doing exactly the same and we don't know about it. So having at least an open research that is equipping us with how this is being done, what are the limitations. We are able to talk about limitations of our research and saying where we are in this research. That's very important for me to actually be able to have this. All the research, all the data sets we do are publicly available to all people in all countries. And to me, that is very critical. Now, is this going to be useful for robot imitation learning? Absolutely. I always have this discussion with friends of whether they want a robot that puts their dishes in the dishwasher or they don't want that. I absolutely want that. So I would love to have a robot that can do some mundane tasks that I would not like to do. I'm still due to kind of paint my porch. And I can't believe that we don't have a robot that can do this, replicable, mundane task. And hopefully some of the data we're collecting is going in that direction.
Great. Anyone have a question? Okay,
No worries.
well, let's thank Dima again.
Thank you.
You need to put your laptop up. Go ahead. Our second speaker this morning is Trevor Wood. Trevor is a technical fellow with the Future of Flight Aerodynamics at GE Aerospace. GE Aerospace is a leading provider of jet engines, components, and systems with an innovation roadmap to shape the future of flight. Trevor leads research teams developing new technologies for future propulsion systems. His work centers on advancing the design and analysis to support the development of the revolutionary innovation for sustainable flight, RISE, and the program's open fan engine architecture. Trevor has co-authored more than 50 patents and interfaces broadly across multidisciplinary organizations within GE Aerospace and its partners. Please help me welcome to the stage Trevor Wood. Thanks.
Thank you very much for the introduction, and thank you all for joining me here this morning. I'm very excited to share with you the cool stuff that we're doing at GE Aerospace. This is a great time for the industry in aviation. We're looking to transform or revolutionize how we power the future of aviation flight. And at the same time, as you are all here at this conference experiencing, is the confluence of this time with the expansive capability in supercomputing and what impact that has in our ability to engineer future systems for these complicated machines. So I want to pull you into my world for a little bit for the first half of this presentation to show you why I'm excited, how we're unlocking answers to questions that have plagued us in turbulence modeling for 100 years, for instance, and how supercomputing is allowing us to really make great progress at the same time that the industry is looking for a dramatic change in propulsive systems. So first, a little bit about GE Aerospace and what we do. So we supply aircraft engines and services for defense and commercial propulsion systems. Today, I'm going to focus on commercial. And over here is kind of a summary of the statistics. We have over last year alone, 3.4 billion passengers have flown on GE-powered engines between GE and CFM, a 50-50 partnership between GE Aerospace and our colleague Safran. At any given moment in time, right now, almost 1 million people are in the air under GE-powered technology. And that is constituted from basically 3/4 of all commercial flights. So with that, what's gotten us to this point has been a wonderful evolution of technology. And it brings about the thought of the responsibility we have at GE Aerospace, along with our partners and partners around the world, in terms of defining what is next. The responsibility for figuring out where is true optimal energy utilization for air travel in the future, the path to sustainable power for air travel in the market that serves this society as shown. A broad overview of applications from regional aircraft to narrow body or single aisle aircraft to wide body applications on the top. I'm going to focus today on narrow body applications down in the lower left. Reason being that this is a hot topic in the industry right now. 10 years ago, Boeing and Airbus decided to re-engine the narrow body market with the Boeing 737 MAX and the Airbus A320neo. Reason being that the industry really needed, with the rise in jet fuel prices starting to contribute on the order of 30% direct operating costs for airline operators, that the industry really needed engine technologies now, back in 2015, 2016, in order to compare to waiting for an all-new narrow-body. Now, airframers are looking to design a new airplane for the future, for decades to come in this market segment, which is growing. And that's looking to be sometime in the 2030s timeframe. And so we're looking at what has gotten us to here, the engine technologies that came into being from the current application of engines here in the middle, how that has evolved from their predecessor, legacy engines, okay? In each case, so the narrow-body engine fleet is served previously from CFM56 that was introduced in the 80s. And in 2015, 2016, we introduced LEAP. And that provided 15% lower energy utilization for the narrow-body fleet. Across the other applications, from regional to wide body, similar story, roughly speaking. 10 to 17% fuel reduction through engine technologies. These technologies come from two key legs of efficiency benefits. One is the thermal efficiency in driving the engine core to higher thermal temperatures with advancements in materials and turbine cooling technologies and compact core technologies. Alongside that thermal efficiency, improvements in propulsive efficiency, getting larger and more efficient fans, pushing us to what the industry calls higher bypass ratio. So bypass ratio is the generation of thrust from larger fans accelerating a large mass of air compared to the mass flow going through the core of the engine, providing power to spin those fans. What we've seen as we go through this is the engineering trends of technologies that got us from yesterday's engines to today's is necessarily asymptotic in nature. So what that means is we're taking a hard look now and understanding the investments needed to get the next 15% improvement is going to be much more involved than the last 15% improvement. So it's causing us to rethink fundamentally, what is the future propulsion going to look like? Are we going to asymptote and keep evolving on the current technologies of turbofans and how we fly today? Or are we really truly committed to evolving to as ideal propulsion system as we can think of? And that led to our announcement of the CFM RISE program. CFM is our partnership between GE Aerospace and Safran, where we are looking for 20% efficiency improvement, fuel burn reduction, energy usage reduction, regardless of the source of energy, through the RISE open fan technology and the suite and portfolio of other technologies in order to get there. So I'm going to talk a lot about the open fan and how supercomputing is being used to help us design that. But really, there's four main legs to the RISE program and a whole cadre of technologies that really is the most in-depth technology development undertaking in our company's history. And the open fan, like I said, is really looking to the ideal propulsor from a propulsive efficiency standpoint, which I'm going to talk about in detail to come here. But the companion to that is a compact core. So driving the thermal efficiency of the core to be more efficient simultaneously with fitting that in a tighter package so that it works properly with the open fan. That's our compact core technologies that work to make the whole package much more efficient. And also, as we look to what is needed for aircraft in the future, we provide power from our engines, both in how the engines run and as well as supplying electric power for the aircraft. And the power demands in the future aircraft is growing. And there's an opportunity now for looking at hybrid electric power systems for both distributing power within the engine more efficiently, so that as you cover across the mission envelope of different operating conditions for an engine, we can save energy by doing this more elegantly through electrically distributed power, at the same time providing more power to the aircraft. Those three legs of the RISE portfolio are fundamentally reducing the energy required to fly people from A to B, regardless of the source of energy. Key component in terms of decarbonizing the future of aviation is also the source of that energy or fuel, for which the fourth leg on the lower right is our push or efforts towards making engines 100% compatible with sustainable aviation fuels, or SAFs. And this includes SAFs in terms of what the industry is evaluating today, and in the longer term, hydrogen as a fuel that has the potential to reduce carbon emissions to zero. So on propulsive efficiency, the trend is bigger and bigger fans. Why is that? Is ideal propulsive efficiency, in order to generate thrust to fly an airplane from A to B, what propulsive efficiency wants ideally is to move an increasingly larger area or mass of air, accelerate more infinitesimally so that you can reduce the amount of mixing losses in the jet stream behind the fan. That's why they are getting bigger and bigger. The problem that's incurred is if you look at CFM56 to LEAP, is as you do that, as you're striving to get more propulsive efficiency, you're scaling up the nacelle. The structure that enshrouds the fan here that you see in silver around the fans on the left, as that gets larger and larger in fan diameter, we're adding weight and drag as this thing is flying at Mach 0.8 at cruise, for instance. And that curbs the trend for which effectively constrains how much propulsive efficiency we can bring to a next-gen turbofan until you consider removing it entirely and allowing an engine under wing to grow a fan diameter much larger and basically leapfrog to ideal propulsive efficiency. And that's what the concept of the open fan is all about. And thereby, that in combination with the other technologies, providing the ability to reach 20% fuel burn relative to today's efficient turbofans and LEAP. So on the left, this is kind of a visualization of how you compare an unducted or open fan propulsion system trying to get to higher bypass ratios, larger fans providing thrust, compared to the asymptotic nature on the lower part of that graph for ducted turbofans, fundamentally because of the scale up in weight and drag associated with nacelle scaling, and installation challenges of fitting the whole nacelle system under wing for a tube and wing configuration like you see on the left. So the way you would roll that up is if you evolve next-gen turbofan technologies on the right, we do the same thing like when we went from our legacy engines to the current narrow-body fleet with LEAP. And we would say you'd have compact core engine thermal efficiency technologies on the dark blue on the bottom, plus a limited reach into higher bypass ratio propulsive efficiency that gives you a limit of where the whole package can be in terms of advancements over where we are today. The open fan, in comparison, provides much greater reach in terms of benefit, largely because of the propulsive efficiency that the open fan can provide. So you might say, well, it's an unducted fan, isn't that just a turboprop? So in some sense it is. It's recognizable to the industry. This isn't really that dramatically new a concept, right? Propellers offer the highest propulsive efficiency for the same fundamental physics. It really is just the momentum theory and the way that works out. However, what happens, or the big distinguishing feature between turboprops and the open fan, is flight speed. So what happens is turboprops are limited to the comparatively slow flight speeds for very good and important reasons. We typically design them for flight Mach numbers of about 0.5. This is half the speed of sound. Narrow-body engines today and aircraft fly at Mach 0.8, much faster, high subsonic speeds, okay? What happens when a turboprop flies faster and faster is the energy you're spending in converting your fuel to spin a turbine to spin the propeller, more and more proportion of that energy is spent swirling the flow and creating angular momentum in the flow behind the propeller. So this is an old simulation of computational models of an installed turboprop on the left, and on the right, 10 years ago, a first generation of an open fan. And so the swirling flow behind the propeller is lost with respect to the thrust, the linear momentum that is in the useful direction of moving the airplane forward. What the open fan does is it applies swirl recovery vanes or outlet guide vanes. This, where the arrow is pointing over here, is stationary vanes that are configured so as to de-swirl that angular momentum provided by the rotating fan in front of it. So it's two components. One is a rotating fan that's designed for transonic Mach numbers compared to turboprops, and the swirl recovery provided by these outlet guide vanes that together allow the open fan to maintain its high propulsive efficiency through to high subsonic Mach numbers needed for narrow body flight in the industry. Any of you might recognize that we've been working on this technology for 40 years. Back in the 80s, we had the unducted fan program that was doing the same thing. But at the time, we were recovering that swirl with a second stage of fan blades that contra-rotated, or rotated in the opposite direction of the front fan blades. And that was because the designs at the time required 2 stages of power to get this level of thrust. And over the generations, every time we keep coming back to this concept, we keep looking and learning ways to make this better. And we've evolved our design to the point where we can get all the power in a single stage of fan blades and have a dramatically simpler architecture with a single stage of stationary Rosen behind to provide that swirl recovery. So that's where we are today. Now, this is all sounds great. The fundamentals are certainly work out. Now, how to actually make it happen is the confluence of 2 teams working together hand in hand to advance the state of the art of this new architecture. Like I said, there's a lot of work to be had. And the 2 teams, if I start on the left, it's the multidisciplinary integration of our teams, which fundamentally are looking at every scientist and engineer on the program is looking to make the engine better from their perspective in terms of their experience and how to make that work. And then we communicate with each other in approximate ways in order to advance at a system level the high-level goals. And you could think of how probabilistic models and where AI and machine learning models can help to streamline with streamlined workflows and probabilistic models to help streamline that communication. And that works in the multidisciplinary optimization frame. Where we are today is we're employing some of those models to do that for certain subspace of the design cases, but where that starts to fall apart on us is when we are doing loops of learning and changing the topology, changing the architecture, the mechanical design, and et cetera, of the whole system. And these are discontinuous changes to the design evolution for which these AI and machine learning models today still are topic of future research, which is an exciting time, but that is currently the state of affairs. And where supercomputing comes in is really adding to the MDAO multidisciplinary design space the third dimension of multi-fidelity, especially in the field of aeronautics and aeroacoustics and so on. And that's really where, talking on the right, is by advancements in the hardware that enables these higher fidelity simulations to be able to ask ourselves questions of the turbulent modeling where we see mismatches in the data that can be uncovered with high fidelity simulations on a supercomputing, at the same time as we're advancing the algorithms to be able to solve the flow physics and simulation of Mother Nature in different ways than we could before on yesterday's hardware, and the people that are all really the agents of change to make this all happen. It's wonderful to me to be at the time where we have these teams working on the problem at the same time, whereas traditionally in our past, we would work the right to lay down the foundational capability to then go on the left. But right now, we have these teams simultaneously working together. And it's through great partnerships where, for example, our partnership with Oak Ridge National Labs, we have a cooperative research partnership as a CRADA, which is really helping to go beyond just supercomputing in terms of cranking out the simulations to get the answers for design derivatives, but building out the ecosystem of supercomputing usage towards our design applications in terms of the pre and post capability around how we use these in our design workflows and to get us smarter in how that applies. So briefly, our journey in supercomputing. Now, we've always used computational models to advance our engineering, right? But if I think of supercomputing specifically, it's really been a short time. If I go back 15 to 20 years, we started looking at the aerodynamic simulation of turbulent flows with simple jet flows. So a turbulent jet flow in the lower left, back when we were at petascale, 15 years ago, we were able to, for the first time in our industry, predict with first principles jet aeroacoustics, how jet noise sounds without tuning semi-empirical models, which was the state of affairs for decades in the field of aeroacoustics. So large eddy simulation of turbulent flow issuing from jets was able to allow us to predict the number of jets through different configurations and different conditions without tuning empirical models. That was kind of our killer app that sort of turned our head to say, now let's apply that to wall-bounded flows. And let's look at unsteady losses in our turbine blades, shock boundary layer interaction losses and dynamics in our fans and compressor blades, so that we could really understand detailed physics that no models before simulation were able to capture the coupling of these fine-scale dynamics with the nonlinear effects of turbulent loss generation and dissipation of energy, all of which are crucial as we're designing these blades. But it was limited to simple submodels, 2D slices through our turbines, our turbo machinery, et cetera. It wasn't until we got to Summit that we were able to take that to the context of a 3D blade and understand what these effects mean in different regions of our systems that we're designing for. And as I'm going to show now, going from Summit to Frontier, it was able to unlock expanding that to even fuller context in terms of the impact it has on the system, and to go from subscale rig tests to flight scale. And this is really the industry challenge, is how we go from designing when we're at an early era of our development of technology and projecting what this means in flight years before we can test it. And what this looks like to us is just incredible resolution to provide the insights to our designers, and to capture and basically bookkeep all the dynamics. And this is an example of an aerodynamic flow model of a compressor, a multi-stage 3D compressor. You're seeing a slice through this, but it's a fully 3D flow solution on the right in large eddy simulation. And on the left is a comparable traditional conventional CFD model using unsteady RANs, which the traditional models average necessarily through the detailed flow of the fine-scale turbulence, and they represent the effect on kind of the local time average flow scenario so that you can carry out your design. Whereas on the right, we simulate the turbulence down to the wall finest scales of turbulence, which is a vast scale of spatio-temporal scales, right? That's why it's been so hard. That's why it's required the advancement of supercomputing to get this. And we can look at this all day, trying to understand how these wakes behind, you have stator-rotor interaction in a multi-stage machine. And the wakes, how they evolve, how they mix, how they interact with downstream blade rows, how shocks are generated and acoustic pressure waves are generated and bounce back and forth and interact and affect the dynamics of the loss generation. All of these things are enormously complex when you consider that this is a three-dimensional flow field across multiple components in the machine. And the joke is it's kind of likening to looking in ultra-high definition televisions from today to, if anyone remembers using TVs in the past where you didn't even have cable and you were attaching an antenna to it and you had to position the antenna the right way just to kind of see part of your image. That's kind of what we think we're looking at. So now let's talk about simulating the engine, right? And like I said, starting with the fan, I'm going to walk through the engine here very briefly. Some of the questions that Frontier has been able to answer for us as we've gone to exascale is taking a full fan blade in 3D. We started with models on Summit that would fit basically a rig scale size geometry. We would call this a medium Reynolds number. So Reynolds number is a non-dimensional comparison of inertial forces to viscous forces in aeronautics. And when you run this in a wind tunnel, this is at a medium scale technology readiness level for the engine. And what happens is when you scale from these Reynolds numbers to what a product for an aerobody aircraft might be, say between 12 and 14 foot diameter, that Reynolds number, you're scaling up much higher in terms of the inertial forces. The length scales become much larger. And what happens in the simulation of turbulence is the breadth of the dynamic range of scales that you're trying to simulate, spatially and temporally, grow exponentially with Reynolds number. Computational cost grows actually with Reynolds number to the 2.4 as an exponent. So it's pretty steeply nonlinear. That's why it wasn't possible before Frontier. And what it's allowed us to do is look at regions of, here you're seeing a simulation where we're highlighting the tip vortex rolling over the tip of the open fan blade, which no longer has a shroud on it, right? So we're simulating the boundary layer turbulence shedding into the wake and the interaction of how that boundary layer is being pulled up into the tip. And you have a fully three-dimensional shear flow distribution that generates and evolves turbulence very differently. And traditional models have to be tuned in a way that there isn't a universal turbulent solution that covers this feature for different designs or different ranges of conditions and so on. So what we can do is we can run wall-resolved simulations, full fidelity simulations all the way down to the wall to provide a data set that we can interrogate and look, and then compare as we look towards reduced models of simulating turbulence known as wall-modeled LES instead of wall-resolved, where we can see where the models work and where they don't so that we can educate running design space exploratory studies using cheaper models with this as a reference for how to make those models work. And when you think about it, going from what we would physically test at a wind tunnel, like say in NASA with a 2-foot diameter rig, we're collecting data from this mid-TRL test and trying to make projections years in advance of building flight hardware before we demonstrate this later this decade on a flight test demonstrator. But the physics of high Reynolds number scaling changes for these different features as we do that. So this allows us to basically, while we're preparing to do these flight tests, we're getting smarter with what blades we want to put on that flight test and make it while we're in the design phase of these blades. That's really the unlock that we see, is we're bringing now much earlier into the design phase the fidelity and the confidence at which we can finalize our designs. If you look across the whole engine, fan and compressor on the left, turbines on the right, the combustor. So looking at the unsteady losses, the aerothermodynamics of the turbines, the cooling flows and how that interact. This is part of the compact core technologies I mentioned at the beginning to make it more efficient, more durable, and fitting in a tighter volume. That gets done there. Basically front to back, all the way down to the jet exhaust, every part of the engine that touches airflow is being advanced through the use of simulation to improve the what we take to test. Okay, so then you can say, you know, the obvious question is, okay, great, now we've got this capability. What would it take to simulate the full aircraft engine? So these are kind of rough order of magnitude numbers that you can think of, where the fan I just showed you was a Frontier calculation. 70,000 GPUs, roughly speaking, you know, it takes a couple months to do that, right? You can basically changes a range of how you might look at the design of one component of an engine between submodels to make something cheap and executable for a number of designs, versus if you're trying to do this in the context of a full engine simulation, you can no longer do a single blade. You'd have to look at the full annulus of blades. Think of the compressor and the turbines, a number of blade rows all interacting at the same time. This gets such that each component through the compressor, combustor, and turbine system is looking at 30 to 70,000 GPUs for a couple months. So that adds up to be, you know, beyond what we can do today. Think of 3 to 4 Frontiers working for a couple months to do an engine simulation. Again, rough order of magnitude, to get proper quality data for engineering design, from stunt calc to real engineering solution. And that's for one condition. We design our engines, takeoff, climb, cruise, and descent, right? The mission envelope, right? So this is well beyond where we are today, let alone if you think about taking that to an aircraft. So the industry challenge we have, and like I showed you, this open fan is an unducted propulsor that now is directly coupling to the wing. So the wing needs to be designed with the fan blowing it. The fan needs to be designed with the wing distorting the flow that the fan sees. It's a fully coupled system. So our challenge, and we're working with our partners and our airframer partners on understanding this. We're building the tools to do that, but we can't do it by simulation alone because of the cost that we have. So we're building models that have been characterized from the component level tests of wall resolve to wall model LES, component by component, so we can do that. So we are running an InSight program this year, partnered with Boeing and NASA, where we're using a representative wing, not the wing that's pictured here, but this is our first ever run of a full-scale Reynolds number simulation of a wing turbulent flow using wall-resolved LES. And highlighted here is, if you look at the wing root junction with the fuselage, the interesting flow physics that develop at that intersection have important consequences on the overall performance of the wing. So getting that right is very important and has been the topic of turbulence modeling for years. And so we're characterizing that with these simulations so as to provide a stepping stone from wall resolve to wall model as we look towards expanding this to doing this problem in years to come. So this is kind of a shakedown test of a low-resolution version of an old open fan design on a representative narrow-body wing, capturing just the topology of getting this to work with our codes today, okay? And capturing the dynamic effects and the full coupling from the fan onto the wing and vice versa. And that's the journey that we are on now, and what we plan to do continuing into year 2 of our InSight program with Boeing and NASA on this, is to capture this so that we can educate ourselves and actually set the foundation for co-design. So propulsion system supplier and airframe manufacturer designing together the fully coupled system that we are looking at here. This is how we are going to improve our confidence years before we can do wind tunnel tests that capture these effects, and years before certainly we take these to flight test demonstrators. So it really is a cool time to be working this. And now, while I'm talking a lot, of course, about simulation and the impact that this makes, it's not to say that tests aren't important. In fact, the process discovery is theoretical advancement alongside with experimental verification and exploration that together get us smarter about what designs to put forward and bring to the market. And simulation is kind of the glue that works with that, allowing us to kind of numerically simulate tests years before so that we can understand our test data better. We can plan how to instrument our tests because we can basically interrogate our simulations in great detail and understand exactly how limited instrumentation in a physical test needs to be optimally placed. And so here's just an example. I think we've run over 350 tests across the RISE program right now. Up on the left is a highlight of our partners, Safran, with Airbus at Onera, have done wind tunnel tests of open fan wing interaction. Running a number of interesting configs there. On the upper right, we're bringing durability tests earlier than we ever have in testing the durability of our high-pressure turbine blades. And we've run over 3,000 endurance tests as of first quarter this year, and currently looking at dust ingestion testing of these turbine designs. Again, educating earlier than we ever have before the next generation of turbine technologies. Ground tests of our hybrid electric system on the lower left, again for the hybrid electric distribution of electric power, and composite tests of our composite fan blades and outlet guide vanes at full-scale mechanical tests of hardware on the lower right. All of these are advancing the technology maturation of all the important components of this new engine architecture. So it's a great time to be working in this field. It's a great team that we're fortunate to work with, both within GE Aerospace as well as with our partners and our partners across the DOE, specifically with Oak Ridge National Labs and our CRADA that we have there, and our colleagues at NASA, and many, many others that are really helping to make this happen. I hope I've given you the sense that, you know, the confluence of time where we're really redefining what is the ultimate propulsion system that we need in the future for sustainable energy in the aviation sector. and how much that delivers. If you think of 20% in fuel burn, and the commercial industry burns something on the order of 3 billion barrels of jet fuel annually, and what saving 20% of that would mean, and what that means to direct operating costs for airline operators in the future, and what this sets us on the path towards a sustainable future in this industry, it's really a wonderful time. And the fact that that is lining up with these huge advancements in computing capability and what that's being able to provide for us in terms of unlocking questions we have in the detailed physics of turbulent flow modeling, aeroacoustics, structural dynamics, and so on. It's really fantastic. So with that, I'd like to thank you for your attention, and any questions that you may have, and feel free to catch me at the break if need be. Thanks.
Yes, go right ahead.
Yes, my name is Detlef Hol. I work for Shell. Shell is one of the larger suppliers of sustainable aviation fuels in the industry. You mentioned you spend most of your time on the turbofan simulations, slicing through the air that the plane goes through. Mm-hmm. You mentioned in passing the combustion process.
Yes.
Of course, that's what I'm most interested in. Does that mean you have it fully under control, it's not worth talking about it, or does it mean it's so hopeless that I won't talk about it?
Well, no, that's an excellent question. So I'm giving you sort of my experience on, let's say, the big piece of pie in terms of the change of this engine architecture, and that's sort of the focus of my teams that I'm working with. The advance of simulation and combustion system has been using large eddy simulation now for many, many years. And so, as I mentioned, sort of in passing from jet fuel to hydrogen combustion, for example, many exploratory studies and simulations included in terms of understanding and unlocking that better. So it is an important area of research. I was just focusing on the fan side. Thank you for the question. Go ahead.
Aditya from Oak Ridge National Lab. Yeah. Thank you very much for the nice talk.
Thanks.
I was wondering if you can speak a little bit about the solver itself, briefly about the kind of discretization, time stepping, and linear solver, if any. What are the challenges there?
You can catch me after. I can give you the references where we've published details on this. But Genesis is our in-house solver, which is a discontinuous Galerkin-based scheme. Variable spatial p-order accurate from second to sixth order, flux reconstruction correction procedure. So it's kind of well-established code, and it's been compared to previous large eddy simulation solvers that we have used in the past. This has really unlocked the capability of really expanding it across the whole reach of applications in the engine. Yeah, thank you.
Let's go over here.
Oh, we'll let Dave go first.
Okay.
He came longer than I did. His trip was longer than mine.
With fan blades, right? David Abramson, University of Queensland. So you didn't say anything about fan blade failure and uncontainment of that axe.
Yeah, so I mean, that's an important component that is integral to our design of this, right? So that's key. I would say that you can think of it as designing a turboprop for Prime Reliant, right? And it's like taking that technology and our experience that we actually have Dowty propellers as a turboprop manufacturer within GE Aerospace, and taking that, the application is to a highly efficient Mach 0.8 aircraft design. So in terms of the containment of a ducted fan versus unducted, you can think of turboprop related certification for Prime Reliance. And we have a much lower RPM and lighter weight fan blades such that the impact energy upon release is much lower than it is a traditional turbofan that is flying at a much higher tip Mach number. So the containment engineering challenge is quite different in that regard. Yeah. Good question, thank you.
So Bill Kramer from University of Illinois.
Yep.
You gave a great presentation about the use of leadership type resources for leadership type computing. But for your design, I'm sure that there's many different iterations that you have to go through and many different approaches. Can you talk a little bit about the other types of resources that you envision needing to get to the, implementation of these? So design studies, You listed GPUs and the needs for what you have. Do they all have to be in a single system integrated together, or can you use other types of combination of GPU to get to your final goal?
Yeah, I guess the scale of the machine is kind of the answer that you almost gave to the question, which is we run sub-problems on a combination of internal and external resources as you're doing design exploratory studies, and then we run the leadership class capability when we're expanding to the furthest reach of high Reynolds numbers, et cetera. So as we're doing our standard designs, we use smaller scale machines, GPU clusters included on this, and basically, there isn't a single simulation that advances your technology. You scale it to right size the problem depending on where you are from conceptual to preliminary to detailed design as you're funneling down your concept space and getting to maturing the technology, and you scale accordingly. But for details, you can catch me after. Thanks. Yes?
Yeah, Chris Hull from Hubie Consulting. I'd like to talk about the hybrid turbine. So I assume that the reason why is to decouple the turbine from the fan speed, so you could vary each one independently. Can you tell me what kind of efficiencies you gain by doing that?
It's, not quite. Think about, the distribution of power in an engine. You have multiple shafts. You have a high-speed shaft connecting high-speed turbine to the compressor,
right,
low-speed turbine to the fan. And we distribute power currently, largely through hydraulic systems, as you think through transient maneuvers and the like across the mission envelope. By scaling up the amount of power generation that we provide to the aircraft, we're using that architecture at the same time to look at electrically distributing power between the spools of the engine, for example, to manage efficient off-design operation. It's not decoupling, as you were getting to.
Okay, thank you.
Yep, good question, thank you.
Trevor, we have an online question.
Okay.
Do you anticipate that machine learning can replace some parts of solver simulations and decrease computation demand?
Now, that's a great question. So twofold. I tried to allude to this briefly earlier, that as we connect surrogates between the detailed disciplines and getting to system-level optimization, that's one key aspect of that, right? And so that is growing and expanding. It needs to grow in terms of the discontinuous or architectural changes as we're early in the design phase. A second component of that I didn't touch upon, but the detailed flow physics that I was highlighting that we're using Frontier to uncover, how does one tune nonlinear turbulence models, nonlinear eddy viscosity models, for example, that doesn't have a universal tuning or calibration to capture each of the flow effects? I think that's a key opportunity for us in the future, to have, in the absence of a universal turbulence model, what is the elegant way to stitch together the appropriate turbulence model so that you can go from high fidelity simulation to enable rapid design space exploration and optimization. So those are the two key areas I see.
Great. Question?
Yes?
Again, John Software, High Performance System Software. My question is about the 20% fuel burn efficiency.
Yep.
How do you measure that when you're changing the kinds of fuel from petroleum to electric and sustainable? And are you measuring 20% reduction in weight, 20% reduction in calories, 20% reduction? What's the metric?
Yeah, so I would say regardless of the source of energy, let's just think of energy regardless of its source, the 20% is associated with what is the thermodynamic efficiency of advancing the cycle in the core, what is the propulsive efficiency in advancing the fan aerodynamic design to ideal high propulsive efficiency. So what we're talking about is the thermodynamic efficiency of energy utilization for the mission of an engine flying a narrow body aircraft. And then your question is, if you swap in a different source of energy, that's, I wouldn't say orthogonal to it, but the first step in decarbonization is minimizing the energy it takes to take a certain passenger count or payload up into the air and transport A to B. And then, the carbon footprint of the source of that energy is the next leg. And there's multiple facets to decarbonizing the industry. What I try to focus on is really fundamentally minimizing the energy required. That's what we what we look at. Good question, thank you. Anything else?
Well, let's thank our speaker again. Great job, Trevor. Please join us for our final set of invited talks in 30 minutes at 10:30 local. We will have a session on big data. Thank you.